Hi, everyone. In this lecture, we're going to continue our conversation on the association between two variables. We're going to learn about simple and multiple linear regression. All right, so first we're going to talk about simple linear regression, which is when you look at the association between two variables. Then we're going to talk about errors in regression. Then we'll talk about multiple regression, which involves looking at the impact of multiple explanatory variables on an outcome variable. With linear regression, we have some kind of predictor variable, and we use that variable to predict a case's score on another variable. And so we come up with a prediction equation to do that, and it helps us to take our data and help it to form a straight line. This regression equation we can use over and over again to make decisions about lots of different topics depending on the nature of our variables. Now, usually when we do this test, which I'll talk about linear regression, we use it to complement the correlation coefficient that we learned about in the last lecture. And so we only use this simple linear regression if we found that we had a statistically significant Pearson's correlation R. Let's look at an example. So we can use a regression line for prediction purposes. So let's say we have this graph here, and it looks at the relationship between degrees Fahrenheit, which is on this horizontal axis, and degrees Celsius, which is on this vertical axis. And you see here we have the dots for our scatter plot, and they kind of line up such that they form a nice little linear trend. And so if I looked at these data, I would expect that our Pearson's correlation R would be significant, and its value would be pretty close to +1 because the data points line up nicely in a line, and we see that as temperature Fahrenheit increases, temperature Celsius also increases. So that tells us that we have a positive correlation between these two variables. And so we can use this line to actually do some prediction. So if I know the temperature in Fahrenheit, I can predict what the temperature in Celsius would be. So I would just go to about where 86 degrees is Fahrenheit, which is about here. And then I'd look to see where that would correspond to on that y-axis where Celsius is. And I would say it'd be somewhere in the 30s or so, maybe 35, maybe 30 degrees Celsius would correspond to 86 degrees Fahrenheit based on these data. So that's basically what a regression line does. It draws a line through our data points, and that line is going to be the best fitting straight line for predicting the value of y, in this case, which is Celsius, from x, which in this case is Fahrenheit. And so we just kind of went through how we would do this. Basically what you do, you draw a vertical line. You'd find 86 degrees on the x-axis, and then we draw a vertical line up to the diagonal line, and then draw a horizontal line over to this y-axis, and we get a predicted value of y of 30 degrees. So again, if our Fahrenheit temperature is about 80 degrees, we'd move up and to the left to see what that is for Celsius, and we get about 30 degrees. And so having that regression line helps us to actually predict what the value would be in Celsius if we know the value in Fahrenheit. All right, so if we look at our graph here, the regression line for predicting Celsius from Fahrenheit, we would be trying to calculate something called y prime. And y prime is the value of y that we get from x based on a regression equation that we would come up with. So in this example, our value for x, which was in degrees Fahrenheit, was 86, and that corresponds to about 30 degrees Celsius. And so that's what y prime would be here, that 30 degrees Celsius. And so we based this by looking at our data points. We had about 6 different data points that we were able to come up with. And so then if we ask about a specific data point that was not in our data, we predict it based on what we know about the relationship between Celsius and Fahrenheit from those other data points. All right, so I want to go back to the marital satisfaction study that we did when we talked about that Pearson's correlation in chapter 13. And if you'll remember, we saw a pretty strong relationship between the two variables from that study. So we had gender role flexibility, that's the husband's gender role flexibility, and the wife's marital satisfaction. And we saw a pretty strong correlation. R was equal to 0.76. And so here's a scatter plot of the data over here. But it's not super obvious where we would draw our line through these data points in order to predict what Y would be. Again, Y is the marital satisfaction, and X is our gender role flexibility. So there's not a clear place to draw that line to predict Y based on what we know about X. All right, so here on the right, we have a couple of potential options for drawing our line, our regression line. So here we drew the line in 3 different places, and it's our job to decide which of these lines is the best one. And the way that we decide is we use something called the least squares criteria. And the least squares criteria say that the line that fits the best is the one where you see as little discrepancy as possible between what the actual Y scores are and what the predicted Y scores are. Okay, so let's look at an example of what I mean by this. So here on the right, we have our data with gender role flexibility on that x-axis and marital satisfaction on the y-axis. And then we have our actual data points. So we have the 6 data points from our study. We have data point A, we have data point B, C, D, E, F, G, and H. So these are the data points from our data. And so then we try to draw a straight line through this as best as possible. And we see, though, that our data points A, B, C, D, E, F, G, and H don't line up perfectly on that line. So B and E are pretty close, but these others, there's a little bit of distance between what the actual data points are and what the predicted data should be if we drew a straight line. And so what we try to do to decide on where to draw the straight line is that we want to see overall where do we have the smallest amount of error. That's what we would call it, error in prediction. The smallest amount of error between the actual data points and what we would predict with our straight line. So we have a decent amount of error here when we look at the distance between C and our straight line. And when we look at point F in our straight line, we have a decent amount of distance too. So that's a lot of error here and also a lot of error here. Some of these others have less error. So the distance between B and the straight line is really small. The distance between E and the straight line is small. So those are small amounts of error. And so we try to use the straight line where we have the least amount of error overall to determine where the ideal regression line is for our data. So when we talk about error in our prediction of the regression line, we refer to it as a residual. And the residual is the difference between our actual score from our data and the predicted score based on that regression line that we draw. Let's look at an example of this. So if we go back to our marital satisfaction study, remember our X variable, our explanatory variable, was the husband's gender role flexibility score. The Y variable was the woman's marital satisfaction score. And then we had the 8 different participants in our study. And so for this study, we had gender role flexibility scores for each of the husbands, marital satisfaction scores for each of the wives. And then we can also come up with a mean gender role flexibility score and standard deviation to go with that mean, and then a mean marital satisfaction score with a standard deviation to go with that mean. And so we could draw a straight line through that data if we plot it and come up with what we would predict the marital satisfaction score to be based on our regression equation that we come up with. And so if we predict, we find this column here has Y prime. These are our predicted marital satisfaction scores. And so what you'll see here that the predicted and the actual marital satisfaction scores are not the same. And so we can calculate the amount of error when we look at the difference between what's the actual and what's the predicted. And that's what we call a residual score. So for example, the actual marital satisfaction score for participants A was 0.8, but we predicted that it would be 1.03. And so that gives us a residual score of negative 0.23. And so we can do that for each of the participants in our study. And then we can come up with a standard deviation for those residual scores as well. So you may wonder how we actually come up with this regression equation that we use to predict y from x. And so in order to come up with a linear regression equation, there are three things that we need to know. We need to know the x value that we want to use to predict y. We need to know something called the slope, and then we need to know the y-intercept. And I will talk about these in the next couple minutes. All right, so let's talk about the slope first. So the slope tells us how much up or down change in y we expect to get for each 1 unit change in x. So if the slope is positive, that means the line is moving up and to the right. If the slope is negative, the line is moving down and to the right. And if the slope is 0, the line is horizontal. So let's say we're trying to look at the association between how much time it takes somebody to commute to work every day and their diastolic blood pressure. The diastolic blood pressure is that number on the bottom. So if you think about sort of 120 over 80 being the recommended blood pressure, the diastolic is going to be that 80. And so let's say we come up with a formula where we say that x is our commute time in minutes, and then our diastolic blood pressure is the y we're trying to predict, so we call that y prime. And let's say we know that y prime equals 1.49x. That 1.49 is what we call the slope. And the slope tells us basically that for every 1 unit increase in x, it tells us what the value of y would be. So for example, here our slope is 1.49. So that means that for every 1 minute increase in commuting time, diastolic blood pressure is going to increase by about 1.49 millimeters of mercury. And those are the units for blood pressure. And if we drew a graph of that commute time and blood pressure data, it would look like this. This is the regression equation we will be drawing. And so this is a positive slope because it goes up and to the right. You'll also notice that it's a positive correlation. So as commute time increases, blood pressure is also increasing. All right, so let's look at another example. Let's say we're interested in the association between how pessimistic somebody is and how long they live. So our independent variable, our explanatory variable x is going to be pessimism. And life expectancy measured in years is going to be our dependent or outcome variable. And we'll describe that as y prime. So y prime is life expectancy. Pessimism is going to be x. And then I'll tell you that the slope is negative 0.35. And so what that means is that for every 1 unit increase in pessimism score, life expectancy is actually going to decrease by 0.35. And we know it's going to decrease because the slope here is negative. So anytime you have a negative slope, that means that you're actually expecting a decrease as x increases. All right, and so here's that data graphed as well. So we see here this graph goes down to the right. We see that as x increases, y is decreasing. So we have a negative slope. You'll also notice that it's a negative correlation as well. So if our slope is negative in general, our correlation is always negative too. So again, if we have an equation where y prime equals negative 0.35x, that means as x increases by 1 unit, y is going to decrease by 0.35. All right, so we've talked about the slope as part of the regression equation. The other part of our regression equation that's important is something called the y-intercept. And the y-intercept tells you where your regression line is going to pass through the y-axis. So if the y-intercept is positive, that means that the line is going to pass through the y-axis above 0. If it's negative, that means the line is going to pass through the y-axis below 0. And so the bigger the absolute value of that y-intercept, the further away from 0 that regression line is going to pass through the y-axis. And we'll look at some examples here. Okay, let's add to our regression line by also including the y-intercept here. So let's say we have a regression equation. Our diastolic blood pressure is going to be equal to 63.5 plus 1.49 times our commute time. So another way to write this would be to say that y prime is equal to 63.5, which is our y-intercept, plus 1.49x, where 1.49 is our slope. You can always remember the difference between the y-intercept and the slope because the slope is always going to be multiplied by x. So the slope always goes with the value of x in your regression equation. Now, again, the y-intercept tells you the value of y when x is 0. So if we were going to plot this, it tells us where the graph crosses the y-axis. And again, the slope tells you that as you increase x by 1, y increases by the value of whatever the slope is. All right, so this is what our graph would look like if we graphed it. So the y-intercept here is the 63.51. And it is right about here. So that's where it goes through 0, where y is about 63 is where our line is actually going to go through 0. And so that's basically what the y-intercept tells us. All right, here's another example with a different y-intercept. So this time our y-intercept is 200. And again, that tells you where the line is going to go through the y-axis. So this is our y-axis here, and our line goes through the y-axis at 200. This is our regression line, and it goes through right here at 200. Okay, so the overall formula for our linear regression equation is going to be y prime equals bx plus a, where y prime is going to be whatever our predicted value of y is based on the value that we're given for x. X is our explanatory variable. So whatever the value is for that, that's going to be the independent variable, the explanatory variable. And then B is going to be our slope. And so what the slope again tells us is that when X changes by 1 unit, Y is going to change by the value of the slope. And then finally, A is our y-intercept, and that tells you the value of y when x is 0, and that shows you where the regression line is going to intersect the y-axis. Okay, so let's go back to our marital satisfaction study. And let's say I tell you that the value of B is this 0.0568, which will round up to 0.06. And then let's say that I tell you the value of A is 0.58. And we just said that the formula for our regression equation is going to be y prime equals bx plus a. So by that logic, if we plug in a and b here, we're going to get y prime is equal to 0.6x plus 0.58. And again, to review what all of this means, y is always our predicted value of y if we know what x is. X is our explanatory variable. So in this case, Y was our marital satisfaction for the wives. X is the husband's gender role flexibility. B is our slope. And so the slope tells us that when X increases by 1 unit, Y is going to increase by whatever the value of the slope is. So here, when X increases by 1 unit, Y is going to increase by 0.06. That's what we see here. And then A is our y-intercept, which is that 0.58. And it tells you the value of y prime when x is 0. And so what it does is it shows you where your regression line is going to intersect the y-axis. Let's look practically at how we would actually use this regression equation to predict y. So let's say we know the value of x. Again, x is the gender role flexibility of the husbands. And let's say we want to use that to predict y. So let's say we know the gender role flexibility of a particular husband is 30. So we can take that 30 and substitute that into our regression equation and then use that to solve for that y prime. So we said b was 0.06, again, that's our slope. X is 30, that's the gender role flexibility here. And then our A value, which is our y-intercept, is 0.58. So we can plug all of that in and solve for y prime, and that's going to be equal to 2.38. And so a man with a gender role flexibility score of 30 is going to have a partner who rates her level of marital satisfaction as being 2.38. And if you remember when we first started this example, we said that marital satisfaction is ranked on a 4-point scale, kind of like your grade point average. So a 4 would be an a 0 would be an F. She rates her marriage as a 2.38, which will come out to be about a C+. So that's one example of how we can use the regression equation to predict the value of y if we know x. So once we have a regression equation, we can actually draw that regression line that can help us to come up with the actual relationship between our variables. And to do that, basically, we need to know two of our data points so that we can connect them with a line. So let's say we decide that we want to predict marital satisfaction based on two different values for husband's gender role flexibility. So let's say we pick 8 as one of those values, and then 38 is the other value. So we have our equation y prime equals bx plus 8 plus a. And so we said that b, again, is our slope, which is roughly about 0.06. It's 0.0568 to be exact. And then we're going to multiply that times the husband's gender role flexibility score, which we said was 8. And then we're going to add our y-intercept, which we know is 0.58. So we're going to solve for that. We're going to get a y prime of 1.03. Now we can do the same thing if we have marital satisfaction. If we have the gender role flexibility equal to 38. So y prime is going to be equal to b, which is our slope, times our gender role flexibility score, which is 38, that's x, plus, again, the value of the y-intercept, which is 0.58. And if we solve for that, we're going to get a y prime of 2.74. Okay, and so if we have two data points, we can take those two data points and then connect them just with a straight line. So let's say we took 8, which was about here for our gender role flexibility, and 38. We could just connect right there to come up with our straight line. And so we can use that line to predict the possible values of y if we know x, if we have a regression equation. All right, so what we've talked about up until this point in this lecture is what's known as simple linear regression. And it involves the relationship between two variables. Now we're going to talk about multiple regression, which is a extension of simple linear regression. Okay, so let's walk through a new example. Let's say I want to determine the cost that it'll take to build a mental health clinic. And so we want to build this new mental health clinic in our city. And we're trying to predict how much that's going to cost. And so we could decide that the best predictor of the cost to build the clinic is going to be the size of the clinic in square feet. That makes sense. Size is going to have a relationship with costs in this instance. So if we wanted to, we could do a simple linear regression analysis here. We could just do the y prime equals a plus bx, where y prime is the cost to build our clinic. X is the number of square feet the clinic will have. And we could just do that. But the problem with that is that we're assuming that the number of square feet is the only factor that determines the total cost, which is more than likely not true. All right, so if we're thinking about the cost to build a mental health clinic, lots of factors can play a role. So things like clinic size in terms of square feet can matter, but also the number of exam rooms you have in the clinic, as well as the number of offices, also play a role. And so we can use something called multiple linear regression to look at the effects of multiple explanatory variables on one response variable. And so up until this point, what we've talked about is simple linear regression. That's when we have one explanatory variable that we use to predict our response variable. But with multiple linear regression, we can have multiple explanatory variables and use that to predict our response variable. So here we have multiple explanatory variables: number of square feet, number of exam rooms, and the number of offices. And we use all of that to predict cost. Okay, so to come up with our regression equation that predicts the cost to build a mental health clinic, let's say we collect data from 200 mental health clinics in the United States, and we use multiple regression analysis to come up with our figures for cost. And in doing this, we factor in the clinic size, the number of exam rooms, and the number of offices. And so here we just have two clinics here that we use of the 200. This is just a sample of what we're using. And for each of these clinics, we have the cost to build, the size of the clinic, the number of the exam rooms, and the number of offices. All right, so we can come up with this for all of our 200 clinics. And let's say we do this and we come up with the following values. So for the cost to build the clinic size, the number of exam rooms, and the number of offices, we can come up with a mean and a standard deviation for all of these parameters. All right, so now we can use these data to build our multiple regression equation. So the regression equation is very similar to the one we would have for simple regression, except instead of just having one explanatory variable, we have multiple explanatory variables. So here, our regression equation could be y prime is going to be equal to a, which is our y-intercept, plus b1 times x1, plus b2 times x2, plus b3 times x3. And here x1, x2, and x3 represent three different explanatory variables. So if we're talking about our clinic example, x1, x2, and x3 can correspond to the number of square feet, the number of exam rooms, and the number of offices. And each one of those explanatory variables is going to have a slope. And so B1, B2, and B3 are going to correspond to the slopes for X1, X2, and X3. All right, so now we can actually perform our multiple regression analysis, and we usually use software to do it. So again, we have our equation, y prime equals a plus b1 x1 plus b2 x2 plus b3 x3. And so this is what we might get from our software. So we'll have our independent variables in one column, the regression coefficients in the next column, and then the p-value that indicates the statistical significance for each of those variables. So in an output, you'll see something called the constant. That is our y-intercept. And so here, that's going to be the value of A. Here it would be 60,102. And then X1 corresponds to our square feet, so that's the size of the clinic. And we get 63 for the value of B1 there. And then the number of exam rooms is our second explanatory variable, that's X2. And we have the slope for that here, that's B2. And then the number of offices is going to be our third explanatory variable, X3. And here we would have B3 here, which is going to be the slope for X3. All right, and so we can take all of that information and actually put it into a prediction equation. So we can say y prime is going to be 60,102. That's our y-intercept, plus 63 times x1. So we have the slope for x1 is the 63.0, that's our b1, plus 15,170 x2. This value here is the slope for x2. Here we have the slope for x3. And so we can put all of this together and use it to predict cost, and that's going to correspond to y prime. All right, so now let's use the regression equation that we just came up with to actually predict the cost of something. And let's say we have data on the number of square feet, the number of exam rooms, and the number of offices. So let's say we have a builder. They decide to build a clinic that's 1,679 square feet, It has 3 exam rooms and 2 offices. And so our goal is to find the predicted cost to build this clinic. And so we have our regression equation, y prime equals 60,102 plus 63 times x1 plus 15,170 times x2 plus 12,000 x3. And so what we're going to do basically is sub in the values that we've gotten here for x1, x2, and x3 to come up with our cost. And so this is again our prediction equation. And here we're going to have y prime is our total cost. X1 is the number of square feet in our clinic. X2 is our number of exam rooms. X3 is the number of offices. And so now we can substitute all of that into this equation. We know the value for the square feet at 1,679 square feet. So we'll substitute that here. We know there's 3 exam rooms, so we'll substitute that in for x squared. And then we know there's 2 offices, so we'll substitute that in for x3, which is the number of offices. And then if we solve for all that, we're going to get a cost of $235,389. And so just like we see in all of our other examples, we can calculate R squared for multiple regression as well. And just like in all of our other examples, R squared tells us the percentage of variability in our dependent variable that it's accounted for by the independent variables. And so ideally, the better your regression model is, the higher R squared is going to go. And so this helps us by doing multiple regression, we can account for multiple variables as opposed to just one explanatory variable. And so that makes it much more powerful than just doing a regular simple linear regression.